All right, it seems like most people have filtered in, so I think we can get started. For anyone who's jumping in over the phone, by the way, just to kind of let you know, it might be hard to follow along with everything that's going on in the webinar, particularly all the screen sharing we'll be doing, showing off a little bit about the ecosystem, and also the demos that Tom's going to be going through. So real fast, just a little bit of housekeeping. I'm going to quickly go over Blazing SQL in Rapids, but this will be shorter than what we've been doing in the past webinars, just because if you're really interested in seeing that, you can go to our website, you can go to our Twitter blog, or you can see any of our prior videos to check it out. If you like this content and want to see more of it, please subscribe to our YouTube channel and our Twitter at Blazing SQL. Those will have, the latest webinars on YouTube, but on Twitter, we'll always have the latest and greatest information that's going on with Blazing SQL in the Rapids ecosystem. It's just where we put everything. And then, yeah, after I go over my overview, Tom's going to go over basically part 2 of the parking spot demo, where he'll take basically everything he did in the first version of this demo, which if you're not familiar with, you can see on our YouTube channel as well. It's called Blazing SQL Livestream #1, and Tom basically walks us through the Seattle Department of Transportation parking data set and how it is that he prepped it for an analysis of which we're seeing the second part of today. And then once he shows us off the hands-on that he's going to be doing, where he's building a regression model and traversing graphs and doing all sorts of really nifty things about making the analysis more involved, he'll be scaling it up on a multi-GPU instance so that we can see how the parking spot demo actually scales up whenever you have to handle much more data or are trying to do prediction with many more features. So you'll be able to check that out. And hopefully we'll be able to finish in time to have a little bit of Q&A. Real fast, some other housekeeping. You'll be able to follow along 100% with this workflow, with the first part of this workflow, the hands-on part of this workflow on app.blazingsql.com. You can create a free user. You will have a private environment that is all of your own, where no one else will be interacting, but the GPU will be a shared resource GPU. So, you know, it's possible to be impacted by nasty neighbors and things like that. So if that happens during this webinar, you'll always be able to redo it later whenever there is less activity happening on the application itself. But yeah, just check it out, app.blazingsql.com. Tom will walk us through how to update the directories in there if you created a user prior to today, which you'll need to do to be able to follow along with the hands-on demo. So as I mentioned, we're Blazing SQL. I'm one of the co-founders. We're a GPU accelerated SQL engine, and we're also really big contributors to the Rapids open source ecosystem. So for anyone who's not necessarily familiar with Rapids and the Rapids open source ecosystem, it's an end-to-end data science stack that is really built around popular APIs and packages that people use for data science in Python. The only difference is that everything's been built to be accelerated on GPUs. Blazing SQL is built on the same exact stack, and we share a lot of the low-level C++ primitives to be able to offer customers a distributed SQL engine in Python that runs off of these data frames. And Dask is what we basically use to scale things up from one GPU or one server to many GPUs or many servers. And so we'll kind of go through all of that during the demo. Real fast, a slide I skipped by really quickly because I wanted to talk about the whole ecosystem is how you can think about Blazing SQL. So Blazing SQL is effectively SQL on data frames. The only difference with our data frames is that they're GPU-backed data frames based off of the cuDF project, which is effectively pandas for GPUs. And this code, if you're familiar with pandas, should look really quite similar to you. We just read a CSV into this in-memory data frame. This is now in GPU memory. We can create tables off of it, and then we can just run ANSI SQL compliant SQL or SQL on those data frames for whatever purposes that we happen to have. Moving forward, just for anyone who's not necessarily familiar with Rapids, before I hand it off to Tom, this is a not exhaustive list of everything that exists inside the Rapids ecosystem. There's actually a lot. What's really important about this slide, though, is basically that everything is built off of this Apache Arrow in GPU memory layer. And this is what the data frames effectively look like. And so that's why SQL is able to to operate on this data frame, or you can have cuDF, which is like pandas, or you can submit this data frame to other libraries and packages. cuML is effectively scikit-learn, re-implemented for GPUs, and we're actually going to be going over some of that today. cuGraph is graph analytics. It's effectively NetworkX, re-implemented for GPUs, and there's all sorts of connectors to PyTorch, Chainer, etc., and visualization. So with all that in mind, I'm going to let Tom just take it away and show off parking spot demo part 2, since that's what we're all here for. And I'm going to let him share his screen. So Tom, can you take over, please?
I will gladly do so. Let me try first. Share my screen. Okay. All right. Let me know if you can see this.
Yep, looks good.
Awesome. Okay. Thanks, Rodrigo. Welcome, everyone. This is the third installment per my count of us presenting the power of Blazing SQL and Blazing Notebooks. So welcome, everyone. If you are not familiar with how to start, you can simply go to app.blazingsql.com. And when you launch this website, you can sign in with your Google credentials, and we will provision a Jupyter Lab, as you can see, running right now. Once you log in, you should see a Welcome to Blazing SQL folder over there. Now, we've pushed some content to that folder yesterday, so there's probably going to be a need for you to update that folder. The easiest way to do this is to launch a terminal. And when the terminal opens, you will see that you are in the root folder. So just change to Welcome Blazing SQL, and then just try to do a git pull. It should automatically, I'm already update, but it should automatically pull the latest version of our main branch from GitHub. If you have problems, if there's any problem with, it tells you that there's some changes already in your folder that haven't been, checked in, you can do git stash and git pull and see if that works. If that doesn't work, the last result solution is to move out from, from that folder, do rm-rf welcome to Blazing Notebooks, and then clone our repository. I wonder, oh, I don't have it here. Clone our repository from Blazing SQL.
Real fast while you're doing that. Yep. I'm getting a question in the Q&A saying that all they see is a black blank screen. I can see Tom's screen. I'm wondering if anyone else is having difficulty seeing the screen. If you are having difficulty seeing the screen, if you can maybe raise your hand inside the participant pane, that'll help us find out. We'll assume that everyone else can see the screen, unless people let us know they can't. So for anonymous attendee, I'm sorry. I don't know what might be the issue.
Okay. All right. So I'm just going to carry over. And then if you guys have problems, please raise your hands. And Rodrigo, please interrupt me whenever there's any problems. Yep. So as I was saying, that the last resort is to remove the Welcome to Blazing SQL Notebooks folder and then just git clone this repo. So this is available at github.com, blazingdb, Welcome to Blazing SQL Notebooks. I will paste that into the chat window just in case, if I can find it. I'm just going to put it here if I can. I don't. Rodrigo, would you mind sharing that with everyone?
Yeah, I'll do it.
Thank you. All right. So I'm going to assume that we are at the same page. So if you go into the Welcome to Blazing SQL Notebooks, navigate to Webinars and Seattle Parking, you should see a notebook starting with 2, and that's pretty much where we're going to live today. I'm going to close this. I'm going to minimize that so to maximize my real estate. Okay, so as Rodrigo mentioned, we already spoke a little bit about parking in Seattle dataset previously, right? So the first webinar that we did was literally about this dataset. I'm not going to go into details about about what this dataset is, but effectively this is every single transaction that happens if you do a use public parking spot in the Seattle city area, and you swipe your card in one of the parking meters. So there's roughly 12,000 parking spots on roughly 1,500 block faces available in this data set, and roughly around 300 million parking transactions annually go through that. What will we use today? Well, we'll use a bunch of stuff. I don't think we need the CUDA cluster anyway, but we will need CuPy, NumPy, cuDF, DaskCuDF, but more essentially, we will be using cuGraph, cuSpatial, and cuML later on. cuGraph, as Rodrigo mentioned, this is already this is the graph network X for GPUs library. cuSpatial, we have, I believe we have John Murray here, who is our geospatial specialist that I like to call him. cuSpatial is the spatial library for doing spatial analytics, spatial operations on the GPU. So go ahead and start this. That might take a little while, but what we're currently doing here is we're loading, of course, all the libraries, but we're also instantiating a Blazing context. We will use the Blazing context to retrieve the data and also use SQL on top of the tables that we will create. And we're also registering the S3 buckets so we can retrieve the data from the BSQL bucket that we have on AWS. For those of you who are familiar with this and how Blazing SQL operates, we will just simply create tables. And we can create tables, as you can see, directly from an S3 bucket. So as I do this, you can see that the memory usage on my cluster is slightly going up and something is happening in terms of the GPU utilization. Over here, what we did, we've effectively created the parking locations. This automatically, as soon as you call Blazing context.sql and then retrieve some data, what Blazing SQL returns in return is either a cuDF data frame. In this case, because we are not using Dask, it's going to be a cuDF data frame, so it's going to be automatically loaded into GPU. If we had a Blazing, a Dask cluster running, and we attach to that Dask cluster, the return object would be a Dask cuDF. And I'm going to show you that later on in the non-hands-on part of the webinar. So first things first, we're going to featureize our parking transactions. What we did previously, we simply said, OK, well, end-to-end goal was to find the nearest parking spots to Seattle Space Needle. What we did, we effectively looked at, OK, well, what is the average number, occupancy at any given spot, at every single parking transaction. And later on, we use the hub-assigned distance from Space Needle to every single transaction, every single parking spot, to determine which parking spots are the most feasible to park on when we try to visit a Space Needle. Now, the problem with that approach is very, frequentist. It's kind of like, it's an average of what we would expect. What we would like to transform to is to kind of create this prediction, like, I have that many parking spots available over there. How many, really, how many, occupied parking spots should I expect at any given point in time when I'm trying to visit, Seattle Space Needle? So this is what we're going to try to do. First of all, we need to create some features for our data sets. So in this case, we will limit the number of transactions to the last week of June. So as you might remember, we have pretty much May and June 2019. We need to limit that a little bit because we are running in the free app, and we have neighbors that will be running on the same server, so we don't want to smash into each other. And for that matter, we will create literally just a single feature, see how much we can get from just literally building a simple machine learning model with a single feature. And the single feature will be, okay, well, at the time minus 1 hour before I'm planning on going there, what was the average occupancy at that particular parking spot? So this is what we are going to use, and this happens effectively here in this particular method, where we take the data frame occupancy date time and we add a time delta 64, and in this particular case we use the previous hour, and we also flag the not outliers. So we've seen that before in the first installment. There are situations where the paid occupancy is exceeding the parking space count, so we will just remove that. So if you run this, you should see, probably, if my memory serves, around, yes, 5 million records without the outliers. So next, every single transaction we see has a timestamp. So we need to aggregate it up to the nearest hour, right? So we extract year, month, days of the month, and hour from our occupancy date time, and then just effectively aggregate that up to and extract, okay, what was, just a reminder, the paid occupancy, this is literally at that point in time when that transaction happened, how many parking spots were occupied on that particular parking spot, which is here denoted as the source element key. So I'm going to run this. This should run very quick, and it shouldn't take too much time. So to prepare the data set for training, as I said, we will use only one feature, and in this particular case, it's going to be this average occupancy prior 1 hour, which is effectively what we've created here. But we will attach that to our parking transaction. So for each parking transaction, yet again, we extract the year, month, day, and hour, and we will look it up in our parking transaction aggregate, right? So we will take the time prior 1, we extract the transaction year and month and day for that, and then just left outer join to the parking aggregation, parking transaction aggregated, in order to carry over this average occupancy that we have created here. And we'll call it average occupancy prior 1 hour. So if you run this, and once this finished, you should see something like this, right? So the first element, we have a parking, parking spot 20,834. There was 5. It was occupied, 5 elements. So five cars were parked at that point over there. This is where that transaction occurred. So it was on the 28th of June 2019, 5:40 p.m. And at between 4 p.m. and 5 p.m. or roughly on average, there was 5 cars parked at that particular spot. For this parking spot, currently at 4:51 p.m. there were 6 cars parked. In the between 3 p.m. and 4 p.m. there were 5, 9 for this parking one, and then in the previous hour it was 7, and so on and so forth. So this is a very, very crude, very simplistic approach, but we are limited by what we are working on right now. This is not to build a perfect model, just making sure that we understand that this is not to build a perfect model. This is more to showcase you that how easy it is to come from something that runs even in on a CPU in pandas, to move this to run on a using cuDF. And in this particular case, we just further refine just drop the drop element key and occupancy daytime, because we don't need that for training. And we're going to free up some memory. You can see that we've deleted some of the release, some of the memory, so everybody can have their turn. So right now we have the data set that's ready for us to use to build the model, right? So we have our label. We want to predict 5, 6, 9, 13, 11 based on the average occupancy prior 1 hour. This is, as I said, this is a very crude model. But let's see what we're going to get out of that. So this is where we move to using QML. QML, as Rodrigo mentioned, this is the machine learning library that is built on top cuDF, and it has a lot of functionality already built in. If you are not familiar with what it can do, you can go to docs.rapid.ai and go to QML to stable or nightly, depending on what you want. And you can see that there's a lot of models already built in. So you have regression and classification. We can click on that. You'll see that there's already a bunch of models that are built in. You have linear regression, logistic regression for classification, ridge and lasso regressions, elastic net, which is a combination of these two, and so on and so forth. There's a bunch of already models built in that run an order of magnitude faster than their CPU counterparts. There's clustering models, dimensionality reduction. I don't know if you guys have heard about UMAP and TSNE. These are the most the recent state-of-the-art dimensionality reduction and manifold learning models to extract useful information from your data and then be able to visualize that. They're already there, and then they're also an order of magnitude faster than running on the CPU. We have time series and so on and so forth. We will also use a multi-node, multi-GPU algorithm later, the random forest, but we will get to that. From QML, you are probably familiar, you might be familiar with the scikit-learn train split, test split. QML implements the same thing, just runs on the GPU. And in this case, we say, okay, well, this is my, this is my features data frame, and this is my, this is my label, right? So we can say this is label. And the train size, we will use 70% for the training and 30% to test our model. So if you run this, you should see that, okay, well, we are dealing with, we're going to use almost 3.4 million observations for training and around 1.5 million observations to test how well our model does. So if you pick into the training X, this is our features table, you can see that there's a single feature, the average occupancy prior 1 hour, to predict our model. And as I showed you, we have, there's a bunch of models for, regression and classification. In this particular instance, we will use the random forest regressor, which is an ensemble model, builds random forests, random decision trees, which in this particular case is indicated by the number of estimators. We're going to build, or the model is going to estimate 10 decision trees. Each decision tree can be or have maximum depth of 10, and the leaf node cannot have less than 100 observations in its group. So let's run this. This should be relatively quick. So if you train that, you can see it pushes the GPU utilization up a little bit, and that's it. So right now we have built a random forest model based on 3.5 million, 3.4 million, records with 10 trees in the forest, and in roughly, let's try to retrain that and see how long it takes. 390 milliseconds. There you go. So 300 milliseconds, 400 milliseconds, and you have a fully working model. Let's see how well it does. So if you use, fit, of course, trains the model, predict based on the testing, feature data frame. We can apply the predictions and the predictions to every single row in that data frame. We have 1.5 million of them. So let's try to see how well our model does. So right now, what happens? We take the testing label data frame, and then we predict X. This should spit out the R squared, which is the common metric for comparing different regression models. Sometimes this doesn't work, so I'm hoping that this is not the case when this happens. If it does, we'll have to rerun that from the top. But as you can see, there you go. Sometimes this happens. So I'm going to rerun this from the top, and this shouldn't take too long. But roughly from memory, if I remember correctly, this particular model with only one feature was around 65% R squared. So we'll see how that goes. Okay. Create a table. This should, okay. Let's do this. Up. Okay. And we are training the model now, predicting. There you go. Okay, 63%. So you can see it's not a perfect model, it's a decent model. But our aim here wasn't to build a perfect model. Our aim was to showcase how to do it and for you guys to help and try. So now that we have a useful model, useful in quotation marks, but we can probably, like, it's better than flipping a coin. It's performing better than the random chance. Let's focus a little bit more about how we actually found the distance or the nearest parking spots that are surrounding Space Needle. So first things first, we did that before. We will need latitude and longitude of every single parking transaction. Parking spot. So in our parking locations, we will extract from the parking location. Let me actually bring it up here so you guys can see parking locations head. Right, so it is encoded in this well-known format point. The first is the longitude, the second element is the latitude. So we're going to extract the long and lat using. So this is something that I think we touched upon a little bit during our previous webinar when we spoke about some functionality for processing strings. In this particular case, we are using extract functionality of the string functions from cuDF, where we pass a regex pattern, and we extract the first or the second element and pass that as a longitude or latitude. So when you run this element, you can see that, okay, our longitude is -1 to 2, 3666, and so on. You can see that this is working. Now, the problem before was that we calculated the distance from the Space Needle to every single parking spot as crow flies. So we use hover-sign distance to calculate the distance between these 2 points. Now, this is not really, accurate, right? We cannot fly. As you can see, this is, let's assume this is the, Space Needle. You cannot really fly through a building here to get to this parking spot. The more, realistic way of dealing with this would be to walk along this road, turn here, and then, get to our parking spot. We don't have that yet, but as I mentioned, John Murray from Fusion Data Science was kind enough to actually take the Tiger Road, data set from King County and he had created a data set that we can actually use in this case, which consists of 2 files. One file is the road graph, and then the other one is the road node. So every single node in this graph is an intersection. So this blue dot here, an intersection here, and the edge is the edge between every single nearest intersection between this one and this one with its length. So we effectively have everything that we need to do this. What we are missing is that in that particular data set, we do not have the parking nodes, and we do not have these points here. What these points are is effectively a perpendicular to the road intersection, the nearest point to the nearest, to the nearest edge in that particular graph. And we're going to do that here. So first things first, let's load the data in. We are loading the road graph. We just casting some data types into the required data types. We're going to do the same for the road nodes. And now we can start adding the parking data, parking nodes to to our data set. So there is roughly 100,000. I think there was roughly 50-something thousand nodes in this particular data set. We're going to offset that with a nice round number of 100,000, and that gives us this is our starting point for adding. So every node that we are going to add to the data set, at this point, if this was the first one that we add, is going to have the 127,380 ID. For the parking locations, we are going to offset that by another 100,000 over there. How are we going to do it? Well, it's a very simple math that I will not go into details by right here. But what we effectively going to do is to find the equation for the line that joins two nodes in our graph, and then find a perpendicular line, equation of the perpendicular line to this line that passes through our parking spot. And effectively, we are going to add this point and the parking spot to our graph. So this is pretty much what happens here. I'm going to start running this while I'm going to explain a little bit, how we do this, because this is going to take probably around two minutes to run. It would be actually good if I actually define this first. OK, so this is running. What do we do here? We effectively implement this in this kernel. We handle the special case where A and B, i.e. the road runs from south to north or north to south, right? So in this case, the projection line is going to be latitude X, and then ref is going to be our latitude. If this is not the case, then we can find the slope. The slope is given by just the formula where we look at the deltas between lats and longs, and that will give us a slope. If the slope is 0, which is hardly, it's hard to, if the lat and y, so this indicates the horizontal line. So if the latitudes are, the same latitude, if it's 0, then we treat that as a horizontal line, and then, lat projection is going to take the lat reference and the lat long reference and the lat x. Otherwise, we will effectively use this formula here. So -1 over a times x plus b prime, and we're going to solve for the b prime, which is over here. And finally, the lat and log projection of our point here. So this is, we are looking for this point here right now in this kernel, is going to be returned and found like this. So what happens here? Now, we enumerate through every single location in our data set, in our parking spot. And what we do in this part here is that we create a data set that finds every single road intersection within a radius of roughly 2,000 feet from the parking spot at in question. And then we're going to find every single additional point that links to would link to our parking spot. So that happens when we apply the kernel find projection. I'm going to quickly touch upon, this is the apply rows method we've used before. It uses the kernel find projection that we have defined here, and then the input columns are defined here, output columns are defined there. The keyword args, so this is our reference, log and latitude, that is defined from our, these are the coordinates for our parking spot. And then what happens is that we're going to have more than one, road within that radius of 2,000 feet. So we need to find exactly which one is the smallest one, and that's pretty much what happens. What happens here? We calculate the distances to every single, additional reference points, and then we are going to add, find the closest one by using the n smallest functionality from cuDF. Finally, we add the nodes to to the parking location nodes data frame that we have, and we add additional location edges to this added location edges data frame. So that takes 2 minutes. This is probably the longest bit that we are going to run here. So you can see that we have, okay, this is our parking spot. So it has a minimum of 200,000. It starts with 200,000 IDs and more. This is it ties to our parking spot ID of 1009. And this is the additional closest point to that particular point. And this is its latitude and longitude. So that's pretty much, that's what the kernel projection found for us. So this is good. This is already what we have. And then the road graph data. These are the additional, nodes that we selected to, to join to these additional nodes. So now we can concatenate both the road nodes with the parking location nodes and the location. Location, this is essentially the dictionary of this with the latitude and longitude of the Space Needle. What we can do here right now is to we add the additional nodes and calculate their lengths, right? So we add Space Needle to the graph in this particular case, right? So we take the Space Needle location and we also add that because we need to have that particular location, that particular node in the graph if we want to traverse that graph starting from Space Needle. So this is pretty much what happens in this case. So now we can create the road graph map, right? So this is super simple with cuGraph. We take the road graph data, and we are going to create the graph from cuDF edge list. The edge list is essentially a data frame with a minimum of 2 columns. One that's the source, the other one's destination. You can specify these, as parameters. If you don't specify that, I believe it defaults to SRC and DST. So if the columns in your data frame are called SRC and DST, you don't have to specify these. But this cell here effectively creates our graph from all of the edges that we appended to the road graph data. And then the SSSP, this is the, I think it's expand single source shortest path, which is effectively trying to find, we are going to start, this is the graph object, and we are going to start from the Space Needle. So node ID for Space Needle is the node ID +2. So this is our starting point. This is where we're going to start. And from all of these distances, we are going to extract only the parking nodes that are within the distance of 1,000 feet. The parking nodes IDX, this is literally when I said like every single parking node will have an ID of 200,000 plus. This is effectively selecting all of these, all of these parking nodes. So we have a data set of roughly 60,000 nodes, and if my memory serves, around, I think, 200,000 edges. It took us, let's run that again. It took us 100 milliseconds to traverse that graph and calculate a distance as we walk through the graph to every single parking spot in that graph from Space Needle. It took us 100 milliseconds to do that. So this is a full list. So we have road graph 227495, and it's within 950 feet away from Space Needle, 994, and so on and so forth. So now we can use the regression model, right? So now we have the list of all the parking spots that we potentially are within the 1,000 feet walking distance from Space Needle. We can apply the regression model that we built. So what we're going to do is that we take the distances, we take the list of the the parking spots that we've extracted from the graph. We will join that with the parking location nodes in order to extract the source element key. And then now we can actually use that to join to our aggregates table again in order to get the average occupancy prior 1 hour. So I forgot to mention that on this particular case, we are trying to visit Space Needle on the 24th of June around 1 p.m. and 20 minutes past 1 p.m. So what this is going to do is we're going to join every single location, every single parking spot that we've derived from from traversing the graph, and look up all the aggregates, how many cars were parked at that spot between noon and 1 p.m. So this is what happens here. You can see we've already extracted the source element key. Occupancy date time is what we expected, and this is the average occupancy prior 1 hour. So now we can prepare this for literally predicting. So we can run these two cells, and we say, okay, well, this is our source element key, and it has predicted occupancy of close to six cars we predict is going to be there, or this is going to be 2 cars, or this is going to be 6 cars again, and so forth. So this is a little bit more accurate than what we had before, right? Right now we can actually predict what is the expected number of cars that we would expect to be parked at that particular spot. And then if we were to join this with our parking locations, we could also see, okay, well, how many available parking spots are there, before we actually move it and select this particular spot to park over there. So that's the usage. That's how we would use the machine learning model that we built, the regression model that we built. I understand that this is very simplistic, but this is just to show you the kind of like, the stepping stones and how you get to this point. You can expand beyond that. If you can actually, launch a private cluster on our, on Blazing notebooks and, take this beyond that. And I'm going to show you in a second my version of that model. And then the final step is the single source shortest path gives you a literally hops between, okay, if you go from this node to this node to this to this node to this node, you will eventually reach to the parking location. So you can actually take that and extract that from that node. So this tells you, okay, we are starting at, this is a Space Needle. We're starting there, so there's no predecessor. Predecessor is the, where would you start? There's no predecessor. We start there, and the distance is 0. So we hop then to node 47828, and that's 276 feet. And then we jump to 127.827. This is for another 400. So this is the cumulative distance. Eventually, we will get to a parking spot. So in this particular case, it will be the parking spot because this is the 200,000 ID, and that's 953 feet. You can see, like, we don't have the Gmaps here. I normally would have a Gmaps running here, but you can actually see that this is pretty much how would you walk to these parking spots had we had this plotted on a Gmap. So this is the end of this presentation. I am going to start a server because it was stopped before, so that shouldn't take too long. But in the meantime, if there are any questions, I would be happy to take some of them while we wait for this to start. This shouldn't take too long. What do you think, Rodrigo?
Yeah, no, it's a great time for questions. There are none right now, but if anyone does have anything, please shoot them our way. In the meantime, there were a couple of questions that we kind of answered through chat, but I can kind of bring it up again.
Yep.
Yeah, everything that Tom is showing is with an open source stack, and so everything that you saw, you can run locally, assuming you do have an NVIDIA GPU.
That's right.
You have the drivers installed, and you have all the dependencies. So here's a question from Alan Reiner. How can you confirm if it's using a GPU? Is there a command to confirm, or does it just not work if there is no GPU? So Tom, could you show your Jupyter lab real fast?
Yes.
There. So on the right-hand side there, you'll see we added a little bokeh utility that has all the GPUs that are running Tom's also typing out a command that shows you information about GPU and how it's being leveraged. So that's how you can see the GPU actually in use. So while you're running all these commands, if you bring up this little dashboard, this GPU resources dashboard, it's actually on the left-hand side. It's right there in the extensions, and you can pop it up and just move the widget pane around. This will not work if there's no GPU.
Thank you. I was just about to say that.
Exactly. So if you're running it locally, if you do not have an NVIDIA supported GPU, this will not run.
And I'm going to add one thing to it. It needs to be a Pascal or above family of GPUs. So any GTX 1080 or 1050 or 1060 will work. Any GTX that is below 1000 series is not.
Mm-hmm. Yep. So your cluster is probably ready.
Yeah,
there you are.
I'm just about to go there.
No, right. Thank you, Alan.
I'm going to copy this while we wait for this to show up. I'm going to clean up my browsers. All right, so this, pay no attention to the man behind the curtain. There you go. Because this is using my old, lab. But what I'm going to show you right now is this. This is literally the, there you go. So when you start this is running on an X large. So we are going to use 16 GPUs in this particular use case. When you start a private cluster with Blazing notebooks, we already instantiate a Dask scheduler that runs on this local host, and you get access to to a Dask dashboard. So if you were to actually copy this to another another tab, you will see the Dask dashboard. I don't know if you guys are familiar with that, but that's what you would see. But good thing about there's a Dask extension for the Jupyter Lab. You can actually observe that as you execute the your code. So in this particular case, I'm going to make it smaller so it's easier to see. In this particular case, what we're going to do is going only through the steps to build the machine learning model. So I'm going to start executing this. That might take a tiny little bit, but it shouldn't be too long. And you can see what's happening while you execute all of these. So right now, what we are doing is we are starting to trying to start the Blazing context executed. I don't know what happened. Why is it? This is showing up there, but it's not showing up here. Somehow lost the connection to this. Let's try that again. There we go. All right. Okay, so you can actually see what's happening. What's happening over here. We are initializing Blazing context on every single worker node in this cluster, right? So sooner or later, there you go. We have the Blazing context ready. So now we can read. We're going to read the same data set that we have used in the previous example, and create the parking transactions, parking locations, and then create the parking transactions table itself. We will change the things around a little bit, right? So instead of using mostly SQL, we're going to show you how to use that with Dask for a twist. So first of all, we're going to create our parking transactions. This is a cuDF, Dask cuDF data frame at this stage. So the .persist, you should start seeing additional tasks showing up. Running on the Dask cluster itself. And when you run this, we have 45 million transactions. I don't know why this is losing the connection to my Dask. There you go. Okay. So we have 45 million transactions in this particular data set. In this case, not only we're going to be using the -1 hour, but also we will use, okay, at this particular point in time, 1 day before, what was the average occupancy, and also 7 days ago. So we're adding a little bit more seasonality into the model itself. So that should be relatively quick as well. And then same as we did before, we're going to mark the outliers. So we remove outliers, those observations that were beyond the parking occupancy. So this is that's effectively doing this for us. And now we will replicate this. We're gonna start appending these, time prior 1 hour, time prior 1 day, and then time prior, 7 days to our, training data set. So I'm going to start executing these steps. You can see this is the, our aggregates. So at this particular point in time, we had, paid occupancy mean and then space count and paid occupancy average there. This is the slight change to what we had before. What I'm doing here is that I'm not only carry over what was the paid occupancy in terms of the actual numbers of there was 3 parking spots occupied or 2.5 parking spots occupied during that particular hour, but I also relate that to how many available parking spots were there on that particular parking spot. And then we are going to run these 2 queries, which effectively brings everything together for the data set for training. You can start to see how Dask takes it upon and then just runs with this, executing everything, and then creating our data set for training data frame. You can see all of this is happening because we have quite a few of this persist. The persist is effectively the call to Dask to, okay, just up to here, I know you've created the graph of, of all the tasks and how they interrelate. Just run this and load all the results into memory so I can use them later. I don't have to start from, and every single time I want to run something, execute that graph from, from scratch. So that's pretty much what's happened here. Right now, we have 42 million records in this data set. The data set for training head looks like this. So we have the day of the week, another feature, hour of the day, another feature, the mean count occupancy, so how many actual parking spots we had occupied at that particular parking spaces we had occupied at that particular point in time. And then this is related, okay, this particular parking spot in the past hour was fully occupied 100% of the time. Like 100% of the parking spots were filled in. So there's what brings me to there's probably only 5 parking spots available at that particular location, right? And then we look at, okay, the day before, what was the occupancy? And then 7 days ago, what was the occupancy around that that hour? There's also, I'm carrying over the parking time limit category. So this is how long you can park at that particular location. That might be a useful, this is something that I was just, playing with. As most data scientists or machine learning engineers do, they test and try. And the beauty of running that either on a GPU or in the Blazing notebook is that you can do this. Like I can literally take this is the train split, the train split functionality for QML is not implemented yet in the multi-node, multi-GPU instance. So I just literally appended a random number to one of the columns and then say, okay, well, just give me 80% for the training and 20% for testing. We don't need that much. We already have 33 million, 33 million rows in the training, 34 in the training, and roughly 8.5 million for the testing. So now we can, this is what our training head looks like. We can clean up a little bit and release some of the memory. And then just pretty much like previously, we have the ensemble, but this is like we are going to use a random forest regressor, but we are going to import that not just from QML, but from QML Dask ensemble. And same deal, we want to persist the data frames, the train X and train Y persist across the workers. So this is what we need to do. In this particular case, since we have 16 GPUs, we are going to estimate 16 trees in the forest. We're going to increase the max depth to 30, and we keep the same minimum number of rows per node. And that should be quite quick. I am going to append the time here. Let's see. So not here, actually not here. I want to append it here. Creating this object sometimes takes a little while, but the training itself should be quite quick. Come on. There we go. So now that's should have happened. We should see some results very soon. There we go. So now we're training. It took us 2.3 seconds on 16 GPUs to chew on 34 million rows and create a 16-tree random forest regression model. So let's see how well we did. This is sometimes because the R2 score is not implemented also in the multi-node, multi-GPU setting. So this sometimes fails, but let's see. Let's see how this goes. I just didn't want to implement this myself. Okay. From memory, I remember that adding all of these additional data and adding all of this additional data and also adding these additional features into the model, it helped us to go from 60, I believe it was 63, 64% R squared to 74, 75, almost 70, almost a usable model that you can use to predict, the the parking spot occupancy for using the Seattle parking data. And that brings us to the end. I know we have 2 minutes left. But Rodrigo, are there any questions that we could, tackle on right now?
Yeah, no, that was awesome. There are no questions up yet, but I mean, what Tom was showing is really what we're trying to show people what's capable, right? You start with a small data set, you iterate on it faster than you've ever been able to iterate on it. Leveraging, the free instances or a single GPU or maybe even a local GPU. But then when you find yourself with challenges or problems that need to scale up to a lot more data, or where you're trying to start taking it to the next level, that's where utilizing Dask and these clusters with the Rapids AI stack really starts to make sense. And you can see how powerful it is and how easily it is to scale up. Obviously, there's still a little bit of work in terms of the whole open source ecosystem to make it so that your single GPU notebook and your multi-GPU notebook look 100% the same, really. But the nature of the ecosystem and how everything's built definitely gives you the capability to do it, to make it work on real production, real use cases. So that was awesome. That was awesome to see. And yeah, there are no more questions coming in. So with that, I think it's a good. Oh, here we go.
There's one. Yeah.
Yeah. So there's 16 GPUs. Actually, these are NVIDIA Tesla T4 GPUs. Yep. So they have 16 gigabytes of memory each, and they're still really quite impressive. In the instance type that that Tom was just showing off in our beta. This is this costs about $16 an hour to run this extra large instance type. If we were using V100s and just paying, bare metal rates, we'd be talking more about $48 an hour. So this is a way for you to get up and running with large scale GPU clusters for really quite a low price point. I'll say I answered that one live. Yeah, okay. So with that, I think, oh, here we go. Here's another one. Nice. Did you say the ML piece is not implemented in Dask? So you had to do your own train/test split. Do you know if it will soon?
I don't know if it will soon, but I would expect it will. And same will go for the R2 score. So the Rapids community and folks at NVIDIA, they're currently working on expanding not only the single GPU, a portfolio of available models, but also taking the currently existing models and then taking them to and scaling them up to run on multi-node, multi-GPU instances. So I would expect it's going to be, just literally a matter of time, and probably shorter rather than later, sooner rather than later.
Another thing I'd like to add to that is, it's an open source ecosystem, so anyone and everyone is welcome to make commitments to the ecosystem to enable features that they're looking for. B, this is the way that companies like ours also pay the bills and keep the lights on. So if that's a feature that's highly important and you want to contract us for that work, that's something that we can also support with. And then someone real fast just mentioned, so Michal mentioned that he was able to get Rapids on WSL2 to work for him. You just need the August versions and onward to work. But it seems like there might be other issues. So WSL2, I tried it out. It didn't work for me the first time when it first came out. I haven't tried it since then just because I've been a little bit too busy. But yeah, it'd be cool to see it running on WSL2. All right. Well, with that, I think that concludes it. If you have any more questions, no, it's just a got it.
Oh, gotcha. All right.
Thanks. So real fast, just to kind of close everything out, you can follow us on Twitter at BlazingSQL. I'm at Rod.Amburu. Tom is at TomicDrabas. You can also reach out to us, Rodrigo at BlazingSQL.com, Tom at BlazingSQL.com, if you have any further questions or anything like that. And please check out the app, get work going there. Let us know if there's anything that it's missing. And yeah, someone's asking if you can share the multi-GPU code, Tom.
Definitely.
So yeah, we'll put it in the
work home.
Yeah, we'll put it we'll put it in the welcome GitHub repo, and we might also try to share it out inside the description of the YouTube video, because this was also live streamed to YouTube, so you can check it out anytime in the future. And we'll put it in the description there too.
Yeah.
So thanks a lot.
Awesome.
Please subscribe to our YouTube channel if you want to see anything else. And really, really excited to show off these workloads. Thanks again.
Thanks,
Tom.